Divide a line segment of unit length randomly into two parts. Find the expected value of the product of the lengths of the two segments. Now for this particular problem, here is a physical interpretation. The unit length can be thought of as a fence of length 1, whatever units you're using for 1 there. And so what you're doing is you're breaking it into a piece x and a piece 1 minus x. When you're finding the expected value of the product, that's the same as, if you have a wall here and a wall here, is taking the two pieces of fencing and making a pen here, let's say for a pig or the like. And it would be the area, the expected area of that pig pen. Of course, the pig would not like this if x were particularly small or particularly large. But nevertheless, that's the physical interpretation of what's going on. The probability density function of x is f of x equals 1 for x values between 0 and 1. And remember here that x is going to be the point at which we break the line segment into two pieces. So here will be one part, and there will be the other part, and we want the expected value of the product. Well, to find that expected value, we integrate, and of course the x times 1 minus x simply gets copied in right here. It gets multiplied by the probability density function, which is 1. And that function is integrated over the support of x, which runs from 0 up to 1. Well, the first thing we're integrating here is x, and when you integrate x, you know you get x squared divided by 2. And then the second thing that is being integrated is a minus x squared, and that will give you a minus x cubed divided by 3. That is evaluated between 0 and 1. When you plug in a 1, you get 1/2 minus 1/3. When you plug in 0, you get 0. 1/2 minus 1/3 is 1/6. So the expected area of this pig pen here will be 1/6. Notice that the largest pig pen in terms of area would be when x is equal to 1/2. In that case, you have 1/2 in this dimension, 1/2 in this dimension. 1/2 times 1/2 is 1/4. So 1/4 is the largest value of the pig pen, but on average, the pig pen will have an area of 1/6. Now, if you wanted to check this out both in Apple and a Monte Carlo simulation, in Apple you would say x is equal to a uniform random variable with parameters 0 and 1. Then you would define a function g, which is x times 1 minus x. And then you would make a call to the expected value function. Here is the random variable x. Here is the thing that you want the expected value of, namely x times 1 minus x, and that would return 1/6. In doing a Monte Carlo in simulation in R, nrep could be set equal to some large number, let's say 100,000. X is a vector getting set equal to R unif. And then you take the mean of x times 1 minus x. That's what you want. The x times 1 minus x is what's in the brackets here. And the mean is accounting for the fact that we're looking for an expected value. When you do that, the first time, you get 0.16671. When you run this a second time, you get 0.16630, etc. You look at these numbers, they are hovering about 1/6, and so this supports the Monte Carlo simulation. Now at this point I am going to hide this, and we will go to, where is the hide? It is here. And we can go back and key this in to Monte Carlo simulation. I'm in R right now, so this time I'll set nrep to a slightly larger number. Oh, let's, instead of 1,000,000, let's go with 4,000,000. You can only push it so hard, but 4,000,000 it should be able to handle. And then what I'm going to do is I'm going to say x is equal to R unif of nrep. And then I want the mean of x times 1 minus x. And in this particular case, again, if I do this repeatedly, I will get numbers that are very, very close to 1/6. Now, I did want to show one mistake here, which is the wrong way of looking at this, which is an easy mistake to make. If I wanted to do this in just one statement, would it be legitimate to take R unif of n rep and multiply it by 1 minus R unif of n rep? And I think there's 3 to close there. And notice that I'm not getting something close to 1/6 when I do this. Instead, I'm getting something that's close to 1/4. So what has gone wrong here is the following. And I'll do that one more time, and you'll see I'll get close to 1/4 again. The simulations which are up at the very, very top up here, all of those simulations involved taking an x value and finding the mean of x times 1 minus x. That's a different operation than two pieces, two uniforms here, which have nothing to do with one another. Here I'm breaking it at some point and multiplying it by 1 minus the value of breaking it at that point, and that is the correct way to run the Monte Carlo simulation. These two down here are the wrong way to run the Monte Carlo simulation.